Hello, this is lesson 10.6, day 2. We're looking at the parametric conics, specifically ellipses, hyperbolas, and circles. We will be using 2 of the 3 Pythagorean identities, and that allows us to represent these conics, the ellipse, hyperbola, and circle, in the parametric form. So recall cosine squared plus sine squared equals 1, whether it's theta or x, or we're going to be representing it with a t. So for parametric, mode or setting or whatever, we use t will be used in place of theta. Because t will now represent the angle instead of theta. So we have, therefore, cosine squared t plus sine squared t equals 1. The second one we use as the form secant squared theta equals 1 plus tangent squared theta. You should recall. If I were to solve that for, get 1 by itself, in other words, I would subtract tangent squared from both sides. So I can see then replacing those with a t, that what we're going to be using for our parametric will be secant squared t minus tangent squared t equals 1. So in general, that's what we're going to be discussing. Recall that circles and ellipses both have the equation with a plus in it. The circle doesn't necessarily equal a 1 unless the radius is 1, but we're going to look at those 2, and then the one that is for the minus, if you recall, is the hyperbola that we're also doing in this unit. So first we're going to look at circles and ellipses. For circles, recall that the standard form of a circle is x minus h quantity squared plus y minus k quantity squared equals r squared. Recall the center is h comma k and the radius is r. So if I were to change it to where the equation equals 1, then I would see that the quantity x minus h squared over r squared plus y minus k squared over r squared equals 1. And using the Pythagorean identity, if I were to compare and say cosine squared plus sine squared equals 1, then I see that cosine squared t would be equivalent to that first whole value, which is x minus h quantity squared over r squared, and then the sine squared t is equivalent to the second portion of that equation, which is y minus k squared over r squared. So if I solve for x and y, it yields a parametric equation. So x equals r cosine t plus h, and y equals r times sine t plus k. These are our parametric equations for a circle. Notice that the coefficient of the sine and the cosine both are the same value, being an r, and then the h and k that are added and are subtracted from those values would indicate our center of our circle. Next, we're going to look at ellipses. Recall again the standard form, and we do have horizontal or vertical. So remember that a squared is the bigger denominator for ellipses, and so when it is under the x portion, then that means it is a horizontal major axis. So I'm just going to, I'll write it over here, horizontal major axis. That's what this one is going to be specifically for, and then we'll derive the parametric equations, and then we'll understand what we switch it for the vertical. So the Pythagorean identity, cosine squared t plus sine squared t equals 1, then I look to see that the cosine squared t would represent the first portion, this first fraction, which is x minus h squared over a squared, and the sine squared t would represent the second fraction in this equation, y minus k squared over b squared. And by solving these equations, we see that, I'll write it here again, horizontal, we can see that x would be a times the cosine of t plus h, and y equals b times the sine of t plus k. Notice that the h is always with the cosine. Remember, cosine represents the x value. Then the sine representing y is, the k is always with the y, just like we know from our equations from before. So if I notice for a vertical what switches, well, the only thing from the original equation switches is the a squared is under the y value. So in just kind of writing this part first, we have y, then the a would be with, or the coefficient of the sine t plus k. Notice again that the sine and the k are always in that same equation together, but the only thing switching is the a and the b because of the equation. So for vertical and horizontal axes, then we have our parametric equations for ellipses. And the last of these type we're going to look at are the hyperbolas. Specifically, again, we have vertical and horizontal. So I'm going to just give the general equation initially here for the horizontal. Remember, we have the subtraction of the fractions. A squared is always the bottom left, and b squared is always the bottom right of these two fractions. But the hyperbola, depending on vertical or horizontal, we look at the first numerator, and if x is first, that's horizontal. And if y is first, it is vertical. So I'm just going to give you this example showing you for the horizontal transverse axis. And we'll just switch that in the equations for the vertical in just a moment. So because of the minus, then we're going to have to use the Pythagorean identity that was the secant squared t minus the tangent squared t equals 1. Because the sine and cosine, squaring those and adding those equal to 1 is the equation when the equations call for an addition of those two, which were only for circles and ellipses. So for the subtraction, we have to use the other, like I mentioned. So if I take this first fraction, which is the positive fraction in front, so that's the secant squared t, which is the x minus h squared over a squared. And the tangent squared t being the second fraction, and solving for the parametric, I'll just write horizontal and then vertical, but we yield the parametric equations. X equals a times the secant of t plus h, and y equals b times the tangent of t plus k. And for vertical, recall that the only thing that changes in the equation, since the denominators don't change, is the numerator. Like I mentioned, if y was first, that is a vertical horizontal axis, a vertical transverse axis, excuse me. So what is changing is what's the first thing, like the y portion being first, that whole that numerator being first over there is going to change the secant tangent portions. So now if the x equals b times the tangent t plus h, and y equals a times the secant t plus k. So we always have the b with the tangent and the a with the secant, but you notice that the x and the y values, those are switched from where they're located with. But remember again, the x and the h are together, the k and the y are together in those equations. Just something to make note of. These are the parametric equations for hyperbolas. On your worksheet for parametrics and conics, worksheet number 2 for tomorrow, we're going to look at a couple of examples. If I have the equation x equals 2 cosine t plus 4, and y equals 3 sine t plus 2. Given these two equations, I can look at my parametric notes to determine, since the coefficients of cosine and sine, first of all, cosine and sine eliminates the hyperbola. It's either circle ellipse, but since the coefficients of sine and cosine have different values, then it automatically means it's an ellipse. Well, so specifically, the first thing you want to do is solve it for cosine and sine. So if I was solving the first one for cosine, not cotangent, excuse me, cosine of t, then I would need to subtract 4 from the x and then divide by 2. So I'm going to go ahead and do all that in a quick way. Sine of t will be subtracting 2 from the y and then dividing by 3. So my equation for the ellipse was cosine squared t plus sine squared t equals 1. So if I substitute these values in, I get x minus 4 over 2 quantity all squared plus y minus 2 over 3 quantity squared equals 1. If I now put it into the form where I'm squaring the numerator and squaring the denominator, you'll notice it comes together very nicely to represent our ellipse equation. So this is our equation, and then they also will want us to graph that. So recall, in an ellipse, we look at the denominators to determine vertical or horizontal. We also can notice from our parametric equations where the bigger number is that we determine our vertical or horizontal. And because it's under the y, that means it is vertical. I'm just going to jot down a few pieces of information to help me graph it. I know the major axis is vertical, and that means that A would be 3 and B is 2. And that my center is HK, which would be 4, 2. If I plot 4, 2, and I go vertically the A amount, and horizontally the B amount, as a quick sketch, I get my my ellipse. That is a vertical ellipse. So you'll have some other examples. There's an ellipse worked out on the worksheet for you, or started for you. You have to graph it. There is a hyperbola worked out, started for you, and you will finish that. But you will see each of these types that I've given you the notes for on your assignment.